Radioactive. Okay, we're back to cover our second lesson on our chapter on nuclear science. In the first lesson, we talked about isotopes, the fact that elements can have different isotopes, which means an element that will have a different number of neutrons. And we gave several examples, such as carbon, which ordinarily has 6 protons, 6 neutrons, but can have 7 neutrons or 8 neutrons, and that some of these isotopes will be unstable and undergo spontaneous nuclear reactions, emitting either an alpha particle, a beta ray or beta particle, and sometimes emitting gamma radiation or emitting a photon. Now, we really focused on the alpha and beta particles, and we'll continue to do so in the rest of the lessons. The question we want to talk about in this lesson is, why are some isotopes stable and some not stable? What's the basis for this? And this next slide gives an explanation for what's really going on. Now, this slide, let me walk you through this, because at first blush it looks pretty complicated. But if you look down at the bottom, what we call the x-axis, this is a number of protons. That is, each number on this x-axis represents a different element. Remember, carbon has 6 protons. So if we looked over on the x-axis to 6, that would be the element carbon. If we looked at 20, that would be calcium. 26, well, that's going to be iron. If we look on over gold, it happens to be 79, lead 82. That's just a few examples of the elements and where they would be on this graph. The y-axis is the number of neutrons. Now, we usually think that there should be 1 neutron per proton, but actually, as you can see in this graph, there are usually more than 1 neutrons per protons in an element. So if we take any particular element, say the one at 20, and if we go up in our graph, we see that we see different dots. Now, what these dots are stable isotopes that can exist for that element. So you can see that element 20, calcium, can have a number of different stable isotopes. That's what the dots are for, stable isotopes. This sort of yellow shaded area is what is called the band of stability. That is, or you might think of it as the Goldilocks zone, where everything is comfortable enough. That is, any isotope of any element that falls within this zone of stability is stable, and it will not undergo a spontaneous nuclear reaction. However, if a particular isotope lies above or below or out to the right of this zone, it will be unstable, and it will undergo a nuclear reaction in order to try to work its way into this zone of stability. Any element with a number of protons greater than 83 over on our x-axis, no matter what the number of protons, will be unstable. That's why the zone of stability doesn't extend above 83. And any element with, no matter what its isotope number, that exists in this upper right-hand area will tend to undergo alpha emission in order to try to approach or to move into this band of stability, this Goldilocks zone. Similarly, any isotope that happens to be in the upper left-hand region will undergo a beta emission in order to try to approach this zone of stability. Now, beta emission essentially is a neutron converting to a proton. So it's sort of a step downwards and to the right. Any isotope that happens to be in the region below the band of stability will undergo another type of nuclear decay reaction, which we haven't explained, but trust me, there are other kind of nuclear reactions called electron capture, what we call K-capture, or positron emission, to try to approach the zone of stability from the other direction. In an electron capture or positron emission, essentially a proton is being converted to a neutron. So this is the basis for why nuclear reactions occur, spontaneous nuclear reactions occur, in order to try to approach and to find their way into this zone of stability, into this very comfortable region. And wouldn't you, don't you in your life want to try to find that Goldilocks zone? So any unstable nuclide will try to undergo one of these types of radioactive decay reactions. And the question is, how rapidly do they do this? How rapidly do they work their way into this zone of stability? And we already previewed this a little bit where we talked about the half-life for the decay of tritium and for carbon-14, and we saw that in one case it's 12.3 years, in other cases it's 5,730 years. So let's talk about this concept of a half-life a little more. So the rate of a radioactive decay will depend upon the nuclide itself. The rate of decay often is characterized by this concept of a half-life. Now, I show you this equation. Tau 1/2 is what we call a half-life. T is for time or half-life. And I show you a relationship 0.693 divided by K. Don't worry so much about what K is, okay? And I show you a mathematical description. The log, that's the natural log, that's a button on your calculator. The natural log of the ratio of the amount of the radioactive material at time t, that's the n with a subscript t, divided by the amount of that radioactive material at time 0, that is when we sort of start the experiment, is equal to minus k times time. Okay, that is the mathematical equation. And actually, this is an equation for what we call a first-order rate reaction. Or sometimes we talk about this as an exponential decay law. Let's not worry so much about the equations, but let's look at the graph at the left to show you what we mean by all of this. The graph on the left shows the amount of radioisotope or radioactive nuclide remaining as a function of time. So let's say we start with a sample of some radioactive material. The drawing just gives you some numbers so that you can easily visualize it. But let's say you start with an amount of this radioactive nuclide. What we mean by half-life is that it's the length of time it takes for half of that nuclide, half of that unstable isotope, to undergo a nuclear decay reaction. So that if we started with 16, after one half-life, we would have 8 left. See, a half-life. Half of it goes away after that length of time. And then, if we wait another half-life increment, we would be down to 4 of these nuclides. If we waited another half-life length of time, another half-life interval, we would be down to 2. And likewise, if we waited one more, we'd be down to 1. But this shows you the mathematical function and what we mean by a half-life. Now, different nuclides decay with different half-lives. Some are very short, some are extremely, extremely long. The next table gives you some values for different radioactive materials. As you can see, the first entry, polonium, an isotope of polonium, polonium-215, has a very, very brief half-life of 0.0018 seconds or 1.8 milliseconds. Very, very brief. Sodium-24, particular radioactive isotope of sodium, half-life of 15 hours, a little over half a day. Iodine-131 has a half-life of 8.07 days, a little over a week. Phosphorus-32, which is used quite often in research, 2 weeks, 14.3 days. And you can tell if you go buy some, you're going to be able to use it for a couple of weeks, and then because it's going to decay and go away as a function of time. Tritium, hydrogen-3 or tritium, 12.3 years. Carbon-14, which we've said before, 5,730 years. And then notice some of the extremely long half-lives of some other nuclides. Technetium-99, 213,000 years. Uranium-235, 700 million years. Uranium-238, 4.47 billion years as a half-life. Thorium-232, 14 billion years as a half-life. So you can see that the half-life for the decay of unstable nuclides can vary over a very broad range of times. Since this decay process is such an important concept, I want to show this slide again of the radioactive decay of a sample as a function of time. Let's say that we start with a 1 gram sample of iodine-131. We saw that it decays with a half-life of 8.07 days. Let's just say 8 days. And so if we start with a sample of 1 gram, like 1 m&m of iodine-131, what this means is that after 8.07 days, half of that iodine-131 will have undergone a decay reaction, converting the iodine to some other element. Now, it doesn't just vanish, it just is converted to some other element. And if the decay reaction is finding its way into that zone of stability, it would form a more stable element. So after the first 8 days, we go from 1 gram to half a gram. If we wait another 8 days, we're down to 0.25 grams. Another 8 days, 0.125 grams. That is, we decrease by half with each increment of a half-life. This sort of process can apply to other phenomena. Let's say that we get our paycheck, and that it's our habit to spend half of our paycheck every 2 days. Terrible habit. So that after 2 days we're down to half. Another 2 days we're down to half again. Another 2 days down to half of that. And after a while we would realize one of two things, right? We either have to start with a larger paycheck, or we got to extend our half-life so that we can pay our bills throughout the month. All right. Another question you might have, and if you think back at our zone of stability and the various elements, is, okay, different unstable nuclides have their own half-lives, but why have they not all decayed and found their way into this zone of stability by now? Well, one reason is that some of these half-lives are very long, so they still haven't all decayed into a stable isotope. But also, there is a continuous production of some of these unstable isotopes. One in particular, which we'll get to later, is carbon-14. Carbon-14 is constantly produced in the atmosphere as a result of cosmic radiation. Well, actually, it's cosmic particles, which are impinging upon the atmosphere, and these cosmic particles will react with nitrogen, converting stable nitrogen into carbon-14, this isotope of carbon. That's just one example of how some unstable radioactive materials are being constantly formed, while at the same time they're undergoing some type of decay reaction to try to find their way into the zone of stability. Okay, we'll pause again for a quiz, and when we come back the next time, we'll talk about some additional nuclear reactions and talk about some important reactions such as the ones that are used in the generation of nuclear power.